Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about In this present video, I am going to describe and share with you all about a very important aspect of ferroalloys production operation. The information and knowledge shared with you all in this presentation is very rare and deep. So please do watch this video very carefully and listen to the message what this presentation is all about. And my dear friends, the topic of the present presentation is the electrodes erosion in submerged arc furnaces. My dear friends, as you are all are aware that the electrodes are the heart of the submerged arc furnace process operation, and slowly the electrodes get eroded and consumed. So what are the factors which control the electrodes erosion in any ferroalloys furnace production operation? I will be describing all about them in this present video. My dear friends, till now I have made so many videos and I know that you all are loving all my videos. So I am very much thankful to you, all of you. And if you are new to my channel or you have not yet subscribed to my channel, I request you all to please subscribe to my channel immediately and also press the bell icon, so that you can get the notifications of all the new videos which are uploaded from time to time very proactively, and you don't miss any information or any video. My dear friends, I am having one of very important announcement for you all. The information which I want to share is that if you want to advertise your products, services, company or anything else on my channel, then please
please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for putting your advertisements in my forthcoming videos. My dear friends, as you all are aware that advertising in the YouTube channels is very common and very fruitful method of approaching to the mass volume of viewers. So you can contact me for putting your advertisements in my forthcoming videos. As you have seen and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. Okay, by now I hope my messages in the previous slides are very much clear to you all. So let's start the present presentation. Submerged arc furnaces for industrial production of ferroalloys do not offer a friendly environment for observation and direct measurements of electrode erosion. The industry reports a certain amount of electrode consumption due to both arc erosion and chemical erosion. The significance of each factor has, however, not been known and is difficult to observe on the furnace. Chemical erosion is dependent on the operation, and high electrode consumption is obviously related to visible flow of SiO gas along the electrode shaft. The arc erosion is probably more constant but is difficult to evaluate experimentally for high current industrial arcs. It is clear that the arc behavior at the electrode is all important when estimating the role of arc erosion in the total electrode consumption. The arc behavior is very sensitive to the boundary conditions at cathode and anode, and therefore considerable work has been put into the development of cathode submodels specifically suited for high current AC arcs, but different approximations are valid than for low current arcs. The results are based on a model that treats anode and cathode in essentially in same way, as the enormous energy impact from the arc ensures that both surfaces emit and receive an abundance of electrons. It does not require the energy balance in the ionization layer to be fulfilled, as there is an abundance of energy from the electric arc that enters this layer. The cathode fall voltage is assumed constant over the cathode surface and determined by the requirement that the total current from the electrode should be equal to the imposed arc current. The energy impact from the arc in the form of radiation and particle flux is taken as a boundary condition for the Fourier equation for heat conduction, which is solved for the electrode body. The arc itself is simulated by a complete magnetofluid dynamic model, that is MFD, which solves the Navier-Stokes equations for transfer of momentum and energy, as well as an equation for the magnetic field. This MFD model provides the temperature at the electrode surface, which determines the equilibrium pressure of carbon that sublimates from the surface. The sublimated carbon is then either transported away or condenses on other parts of the electrode surface. Results from this model predict an arc attachment of a larger diameter than the arc itself, in addition to a negative anode fall voltage. It also implies that electrode erosion is highly dependent on the arc current, the number of arcs burning in parallel, and the geometry of the surface. An electrode model that solves for the current distribution within the electrode and studies the resulting mechanical tensions in the electrode was developed in parallel to this work. There, an upper limit to the time an arc may burn at a certain location depending on the current it carries is established. Now let us study about the general cathode spot theory. If there initially is a void body of plasma at local thermodynamic equilibrium, that is LTE, and suddenly a part of it is surrounded by an isolating wall, the wall will initially be bombarded and charged up by fast moving plasma electrons. The negatively charged wall will then repel approaching plasma electrons and attract ions, thus forming a space charge sheet that shields the plasma gas from the effect of the negatively charged wall. Approaching plasma electrons will not notice the wall before they enter the space charge sheet, but as they penetrate the ion layer, the shielding effect is reduced and they are slowed down by the electric field. So this is the picture which depicts, first figure 1 depicts the schematic drawing of a space charge sheet, and figure 2 depicts the current components in the cathode model. You can pause the video and observe this picture very carefully. Okay. For an isolating wall, the potential drop in the sheath is exactly high enough to ensure zero total current. When a net current is applied upon a plasma contained between two walls, it is natural to assume that the potential fall is adjusted such that there is a net charge exchange between the plasma and the wall consistent with the applied current. The thickness of this space charge sheet is approximately 25 lambda d, which is close to 1 micrometer and orders of magnitude smaller than the thermal boundary layer, which in the case of an industrial arc is close to 500 micrometer. My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on. The AC cathode anode submodel, that is CASM, to be described is based on the following assumptions. The cathode current density J is composed of three components. First, thermodynamically emitted electrons Je, ions from the plasma that reach the cathode surface Ji, and finally plasma electrons that pass through the potential barrier and reach the surface JEPL. The models are to a certain extent based on ideas appearing in Neumann's theory and Benillo's model for low current DC arc cathodes. When a body is sufficiently hot, a fraction of its electrons have kinetic energy high enough for them to overcome the energy barrier called the work function phi, which traps them in the body. The thermodynamic emission current density is given by the Richardson-Dushman equation as this is the equation, Richardson-Dushman equation. Where Tc denotes the cathode surface temperature, E is the electronic charge, phi is the thermodynamic work function, Kb is Boltzmann constant, and delta phi is the Schottky correction. The factor F in the Richardson-Dushman equation is a scaling factor accounting for the fact that a thermodynamically emitted current with the theoretic value of F is equal to 1 has never been observed. According to Fender et al.'s estimate, F is equal to 0.5, which is used in this work. The hot plasma gas contributes with electrons that diffuse over the cathode fall potential UC and enter the cathode. The counter diffusing plasma electron current is given by this equation, equation 2 and equation 3, where Ne0 is the electron density at the edge of the space charge sheet and Ce is the mean electron velocity in each direction. Benilov et al. Reported a solution for the plasma sheet equation that leads to the following expression for the current density of plasma ions towards the surface. So this is the equation given by the Benilov, where dIA infinity is the ion atom diffusion coefficient, Kr is the ion electron recombination rate coefficient, and Th the heavy particle temperature, all evaluated at the edge of the ionization layer. In conventional cathode models, it is assumed that the energy balance for the ionization of atoms by emitted electrons is fulfilled in the ionization layer all over the cathode spot. This is the limit of the self-sustained cathode spot, which does not receive energy from the arc. That approximation is valid for low current arcs. From that energy balance shown in equation 5 in the next slide, the radially dependent cathode fault voltage UCR can be determined. So this is the equation 5. Here Je and Ji represent the electron and ion current densities in the near cathode layer, and Ui is the ionization potential. Thermionically emitted electrons are accelerated over the space charge sheet potential fall UC. The thermionic electrons are emitted with their two-dimensional enthalpy in equilibrium with the cathode body, but need to be heated up to the plasma temperature to be in thermodynamic equilibrium. The energy supplied by the thermionic electrons is used to ionize atoms and bring the electrons excited from the atoms to equilibrium with the arc plasma. The counter diffusing electrons must overcome the space charge potential and carry a two-dimensional enthalpy to the cathode. The cathode spot of a high current arc is, however, dominated by the arc, so the limit of a self-sustained cathode spot unaffected by the energy flux from the arc expressed in equation 5 is not valid. The diffuse spot cathode anode submodel, that is CASM, described and used in this work is based on the observation that in a relatively short high current industrial arc, the energy supply from the arc is so overwhelming that it is not possible to divide the cathode and the arc into two separate energy domains that do not exchange energy. It cannot be required that thermionic electrons accelerated through the cathode fall supply all energy required to sustain the arc spot, as the radiation from the arc and the abundance of much more energetic plasma electrons strongly contributes to the ionization of neutral atoms and equilibration of colder electrons. This means that instead of two separate energy balances, equation 5 on the one side and the MFD transport equations for the arc on the other, an energy balance for the whole system must be solved within the MFD model. In the CASM only the energy balance for the electrode itself is being considered. The heat flux into the cathode anode body must be tagged from the arc by a boundary condition for the arc model. In this new model, cathode and anode are considered to be formally identical and the total current balance is fulfilled at any time for both cathode and anode. This means that the cathode as well as the anode thermodynamically emit electrons consistently with their temperatures and that they are both bombarded with plasma electrons and ions dependent on the temperature of the plasma next to the electrode. The difference between cathode and anode is only that the net current is negative in the cathode half period and positive in the anodic half period. The cathode anode fault voltage, here termed UC for consistency, is determined by solving equation 6 for the given current at each time step. So this is the equation number 6 which I have just mentioned. This means that the potential fall is adjusted such that there is a net charge exchange between the plasma and the wall consistent with the applied current. Radiation fluxes and plasma temperatures are obtained from the arc simulations. An iterative procedure is used to couple the MFD arc model and cathode anode model. In the simulations, it is assumed that the cathode anode body is a good current conductor as compared to plasma. It is also assumed in this model that UC is constant over the surface. An extension to AC is accomplished by imposing a periodically varying arc current. The non-steady two-dimensional axisymmetric Fourier equation is solved for the electrode body using the heat flux in equation 7 as a boundary condition to obtain a periodically varying cathode surface temperature, that is TC/RT. The computational domain is assumed large compared to the cathode spot radius, that is 0.1 meter in the radial direction, and to the thermal penetration depth of 50 Hz temperature oscillations, that is 1 mm in the axial directions. As a boundary condition, we need an expression for the heat flux. So this is the equation number 7, which is the expression for the heat flux. Radiation from the arc is taken into account and sublimation is calculated according to the Clausius-Clapeyron equation for the equilibrium vapor pressure of carbon as a function of temperature given in equation 8 and the Hertz-Knudsen equation for the maximum evaporation rate from the surface in equation 9, which provides the mass flux in kg per square meter second. So these are the two equations which I have just mentioned, equation number 8 and equation number 9. For carbon, H vaporization is equal to 716.68 kilojoule per mole and C1 is equal to 2.29 into 109 bar, provides the equilibrium pressure in bars. The complication in using the Hertz-Knudsen is determining P star. If the surface temperature is below the sublimation point defined by the ambient total pressure PA, the value of P star will be somewhere between P equilibrium and the partial pressure P0 of the cathode material, that is carbon in the bulk. Where in that interval the value lies depends on the dominating mass transfer resistance in the system. An equilibrium will be established between the sublimation rate and the removal of sublimated atoms. In the case of diffusion control, the mass transfer will be slow and P star will assume a value close to P equilibrium. The evaporation kinetics expressed by equation 9 is the rate controlling mechanism. The value of P star be closer to P0.
Before proceeding, if you like my content and have not subscribed to my channel till now, then please subscribe to my channel so that you can watch all the videos available in my channel list, and also press this bell icon so that you can get the notification of new videos promptly and don't miss anything. In case you want to thank me and support me so that I can get further motivation to do better in future, you can just simply send me this special thanks, super thanks, by selecting any of this amount of your choice, whatever you feel like suitable to you. You can just buy this and send to me. This will help me to do further better. You can select any of the payment methods of your choice and then send me. This will motivate me to do further better in future. Thank you.
The second case is when the surface temperature rises above the sublimation temperature at P8. Then P star will assume a value close to P8. A jet of carbon vapor away from the surface is formed and the mass transfer is limited by the fluid mechanic resistance to that jet flow expressed by the pressure drop P star minus Pa. In this work, the transport equations for carbon in the electric arc region have not been solved, and therefore some simplifying assumptions were made. Primarily, equation 9 was written in the following form. So this is the modified equation number 9, where the factor C2 in the Hertz-Knudsen equation is between 0 and 1. C2 is a measure of the mass transfer resistance from the surface. Alternatively, this resistance could be expressed by a mass transfer coefficient which will depend on the local flow velocity. The value of P star was taken as the ambient pressure Pa 1 bar in the areas where the surface temperature exceeds the sublimation point, and also in areas where the gas flow comes directly from that area. For that purpose, the gas flow obtained by arc simulations was analyzed in order to determine in what area the gas at the surface is brought directly from the hottest part of the cathode spot. It is assumed that where a sublimation jet is present, surface temperature above the sublimation temperature C2 is equal to 1. In the area of oversaturated gas, C2 is equal to 0.1, and elsewhere P star is equal to 0, as there the gas temperature is below the plasma temperature and all vapor atoms have reacted and formed molecules. The choice of the factor C2 is equal to 0.1 is derived from an estimated average value of the mass transfer coefficients. A sensitivity analysis in the following section shows that the results are not overly sensitive to the choice of this value. The variation in erosion is of 30%. As shown in figure 4 in the coming slides, for a 51 kA arcs is not more than may be expected from other error factors. The order of magnitude stands unaltered and the validity of qualitative results is not compromised. The electromagnetic equations are not solved for the electrode body and therefore ohmic heating in the electrode is disregarded in this model. Results shown in figure 10, which are coming in the next slides, demonstrate that it is not at all insignificant. In fact, ohmic heating limits the amount of time the arc can burn at each location to seconds dependent on the current magnitude. For the cathode spot behavior, while the arc is at a certain location, the ohmic heating within the electrode is, however, insignificant. The abundance of energy provided by the electric arc is such that the energy balance in equation 5 is not fulfilled, separated from the arc. But as the heat flux by particle impact in equation 7 includes heat transport due to ambipolar diffusion and heat flux due to the current, the boundary condition for heat transport in the plasma must be included as a source or sink term in the MFD arc model. This source term, which is included in the cells next to the cathode anode surface, has the form this particular equation. Notice that the thermionic work function phi terms do not appear in this equation and phi is exclusively a material property which determines the energy of an electron within the material as compared to a free electron. The electric arc is not directly influenced by the work function except by phi's effect on the current density of emitted electrons. The same equation applies at the anode. My dear friends, now I am going to present some very important figures related to this project. So please do observe all the figures and their detailed explanation follows in the later slides. So this is the figure 3rd. Electrode erosion in metric tons per 24 hours as a function of RMS arc current. At the moment you just need to observe the images, and when in the later stages of the presentation I will explain all the details about these pictures, so you have to correlate that time. And this is the figure number 4, which depicts electrode erosion for different selections of the mass transfer rate coefficient, that is C2. The results are obtained for a 51 kA arc. Moving ahead, so this is figure number 5. It depicts current density as a function of distance from the symmetry axis for an arc carrying a RMS current of 21 kA. Black lines for the anodic half period and grey for the cathodic half period. This is yet another image, figure 6, which depicts current density as a function of distance from the symmetry axis for an arc carrying a RMS current of 42 kA. Please do remember the difference. First one was for 21 kA, this one is for 42 kA. Black lines for the anodic half period and grey lines for the cathodic half period. So these are two pictures. Figure 7, this is current density as a function of distance from the symmetry axis for an arc carrying a RMS current of 81 kA. same as black lines for the anodic half period and grey for the cathodic half period. Next figure depicts current. Figure 8 depicts current voltage characteristics for AC arcs as calculated by an MFD arc model. So this figure 9 depicts current components and voltage development over a period for a 21 kA arcs. Figure 10 depicts heat flux from different sources and erosion over a period for a 21 kA arcs. Next figure 11 depicts current components and voltage development over a period of 42 kA arc. Figure 12 depicts heat flux from different sources and erosion over a period for a 42 kA arc. Figure 13 current components and voltage development over a period for a 81 kA arc. Figure 14 heat flux from different sources and erosion over a period for a 81 kA arc. Okay, now let us have some discussion about the simulation results. Energy flux from the arc is by radiation and the kinetic energy of particles, and cooling is by black body radiation, electrode material evaporation and heat transport into the electrode body. All these simulation results are based on the figures I just represented in the previous slides. It has been shown that heat transfer into the electrode is comparatively very small, order of magnitude 20 kW, due to the relatively low heat conductivity of the carbon material and the limited temperature gradients. Heat generation within the electrode body due to ohmic heating is, however, a considerable contributor, and that heat can only be removed by heat conduction. The temperature within the electrode body cannot, however, rise much above the sublimation point for carbon. Therefore, the length of time when a stationary arc may burn at a certain location is limited and much shorter for high current arcs than for lower current arcs. Simulation results shown in figure 3. My dear friends, you have to just correlate the previous figure number 3, which I mentioned earlier. Simulation results shown in figure 3 also indicate that the electrode erosion increases more than linearly with increased current. The erosion from an 80 kA arc is 1.7 tons per 24 hours, while splitting that arc into two parallel arcs of 40 kA will result in an arc erosion of 0.64 tons per 24 hours divided between the two arcs. For an industrial furnace, a typical electrode consumption on an electrode carrying a typical current of 120 kA may be close to 1.5 tons per 24 hours. Measurement on a ferrosilicon furnace indicate that 20 to 40% of the phase current bypass the arc and pass through the charge in the lower regions of the burden, where the carbon materials have formed well conducting and sintered silicon carbide, that is SiC. This configuration is schematically shown in figure 15 in the next slide. So this is the figure 15, which shows a schematic drawing of a configuration with conducting charge resistance in parallel to the arc. Assuming an arc current fraction of 2/3 with the other 1/3 passing through the charged materials, simulations for a single arc indicate an arc erosion rate of 1.7 metric ton per 24 hours per electrode, while two parallel arcs would lead to a total erosion of 0.64 metric ton per 24 hours between them. As chemical erosion is by most furnace operators thought to be the dominating contributor and the erosion varies greatly with furnace operation, raw materials and segregation patterns, these observations correspond better to a multiple arc configuration. Simulations on high current AC arcs indicate a rising current voltage characteristics for arcs carrying more than 7 kA, which means that splitting a high current arc in two or more will decrease the voltage required. Figure 8 demonstrates this for MFD simulations using the boundary conditions presented in Figure 7. Any physical system strives towards reducing its resistance, and according to Knopfmann's stability criterion for DC arcs, a rising current voltage characteristic leads to a stable formation of more than one arc. If Knopfmann's stability criterion is applicable to AC arc as well as DC arcs, two or more arcs burning in parallel is a likely configuration. A sensitivity analysis for the selection of the mass transfer rate coefficient C2 defined in the previous section shows that the erosion has a minimum close to the value selected. Reducing the mass transfer rate will reduce the carbon vapor recondensation in the system, and increasing it will increase the sublimation at surface temperatures below the sublimation point of 1490 Kelvin. The results from this analysis indicate that the sensitivity of the total erosion to the selection of this parameter is of the order of 30% and within the limits of the expected errors of other uncertainty factors. Figure shows the results from such analysis for a 51 kA. You have to correlate again, my dear friends. Previous figure number 4, previous slides. Figure 5, 6 and 7 show the current density distribution as a function of distance from the symmetry axis at even time intervals. I have just explained it during that figures. It is seen for the 21 kA arc, the current distribution in the cathode half period is quite smooth and the density always positive. For the 42 kA arc, a drop in the center is seen for the current density, and for the 81 kA arc, the central current density is actually negative in the cathode half period. I am just explaining what I had earlier mentioned during the figures depiction. These are all the explanation of the pictures. This is due to the high energetic plasma electrons that penetrate the voltage barrier. Figure 9, 11 and 13 show the total current and current component development as well as the voltage barrier for RMS arc currents of 21, 42 and 81 kA respectively. It can be seen that the total current is the sum of the three current components of different directions, that each is larger than the total current. The size of the current components as compared to the total current gets more exaggerated as the total current is higher. As previously reported, the cathode and anode fault voltages are of the same sign and will almost cancel out as contributors to the total arc voltages. Figure 10, 12 and 14 show that the heat flux to the surface and the contributions of radiation, black body radiation as well as heat transfer by particle impact. The contribution of sublimation and condensation are included in the particle impact heat transfer. The erosion rate in the units of metric tons per 24 hours is included in these figures that are for 21, 42 and 81 kiloampere arcs currents respectively. The erosion takes place primarily in the anodic half period. For the lower current levels, there is seemingly no erosion in the cathode half period. This is probably not a precise result, but a consequence of the simplifying assumptions. However, the tendency is clear: the anode half period causes much more wear than the cathodic. Now we are approaching towards the conclusions, so have patience and please observe the conclusions which I am going to describe now. An attempt has been made to evaluate the role of arc erosion in the electrode consumption in industrial submerged arc furnaces for production of silicon and ferrosilicon alloys. It has always been a matter of discussion how much erosion is caused by the electric arc itself and how much is due to chemical reactions with raw materials and gas that leaves the crater. Simulation models that describe both the electric arc and the arc attachment to the electrode are used in this endeavor. The diffuse spot cathode anode model CASM deviates in important aspects from other cathode models previously reported in the literature. Most existing models have been made for low current DC arcs where the cathode spot must be energetically self-sustained and no energy is extracted from the arc itself. The novel model used in this work represents the other limit. The cathode anode spot is dominated by energy impact from the arc and must be included in the energy balance for the arc itself. An improvement in the model would include coupling the MFD arc model and the cathode anode submodel and solve both models simultaneously. The transport equation for the vaporized electrode material should then be solved within the MFD model. Although the CASM has not yet been fully integrated into the MFD arc model, the tentative iterative results indicate a much lower cathode current density than previously assumed and a much smaller cathode fall voltage, which indeed has the same sign in the anodic half period. This means that when considering the total arc cathode anode system, the voltages for the cathode and anode almost cancel out. A negative anode fall voltage has previously been suggested by Fender, but the standard assumption is that cathode and anode fall voltages add up. The relatively low current density gives rise to a cathode spot wider than the part of the arc attached to it. Such wide cathode spots have been observed and discussed on some occasions. The erosion rate depends highly on the arc current. Doubling the arc current more than quadruples the erosion rate. This supports that it is not unlikely that there is more than one arc burning in the craters of submerged arc furnaces, a hypothesis which primarily was based on Knopfman's stability criterion and the rising current voltage characteristic displayed by the arc. Other observations that support this opinion are the rising current voltage characteristics for high current AC arcs and the ohmic heat generation within the electrode body close to the arc attachment reported by Paulson et al. For a Soderberg electrode in an industrial furnace producing ferrosilicon 75% grade that carries a current of 120 kA, a single arc in the crater, the model results would imply that the erosion would count for electrode erosion comparable to the total electrode consumption for a stable, well-operated furnace. Only 40% would be attributed to arc erosion if two arcs do the job. Furnace operators know that segregation in the furnace, changes in raw material and SiO blowing along the electrode can lead to large changes in the electrode erosion and probably find the later figure easier to believe. Interpreting the results, one should also keep in mind that uncertainty in parameter determination may lead to an error of approximately 30%.
Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel, and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.